So with the counter design, I want one of you guys to uh, think about an arbitrary sequence of outputs that you would want your 3-bit counter to have. So the goal is to design a completely new counter with respect to how your you desire, right? Like let one of you decide how you want to count. So the goal of this is to design a counter, let's say 3-bit, right? So it only has a 3-bit output, and Alan has already picked up a sequence. So I'm going to say design a counter that outputs the sequence. Alan says 5432170. So 5432170. After 0, what is after 0, Alan? Is it back to 5? All right, so after that it repeats. And I hope you guys see that we have skipped a state here. So based on the problem, we have skipped one state, which is 6. We are never reaching the 6 value for the counter. So we have 0, 1, 2, 3, 4, 5, and 7. We don't have 6, which is absolutely fine. So that's our goal. That's what we are going to design. And I also want you to pick one more thing, a flip-flop that is going to get this done. So you have D, T, and JK. Which one of this do you want to design this counter? Somebody else can choose the flip-flop as well. Who wants to pick the flip-flop? JK, D, or T? Those are your 3 choices. Ryan says JK. All right, let's pick JK flip-flop for this example. So you have picked up very nice. Everybody wants to do JK. All right, JK flip-flop to design this counter. Step number 1. Is to draw the state diagram. And if you want to draw the state diagram, we are going to see how many states do we have. So let's see, 1, 2, 3, 4, 5, 6, 7. This particular counter has 7 states. Which implies that we are going to use 7 circles to indicate the states. And then we are going to connect them with arrows to indicate state transitions. So on the next slide, I'm going to complete this step. And I have the counting sequence from here. So I'm going to add this. I need 7 circles. Let me draw the circles in black. So let's see. I have 1, 2, 3, 4, 5, 6, and 7. I think that's it, right? I've got 7 circles here. And let me call these guys the states. What are those states? You started with I think 5, right? 5, 4, 3, 2. Okay, so 5. 0, sorry, 1, 0, 1. Then you said 4. Then you said 3. Then you said 2. Then 1. Then 7. Then 0. And then back to that. Right. Now, next step is to connect them with arrows to indicate the state transition. Right. So let's see. I'm going to use blue arrows. So from 5 it goes to 4, to 3, to 2, to 1, to 7, to 0, and back to 5. So I've got my states laid out over here. That's my state diagram, right? So that completes step number 1. Draw the state diagram. My next step is to draw the state transition table. So step 2 is going to be over here. Let me add a slide after. Yes. Step 2. Draw state transition table. So for a state transition table, I need 3 things essentially. One is the current state of the counter, and notice I'm designing a 3-bit counter here because my count never exceeds 7, so I can do this using a 3-bit counter. Those 3 bits are essentially the flip-flop outputs, right? The state is the flip-flop output. So current state, and then I have the next state here. All right, so I'm gonna need to move this slightly over there, need to move this slightly over here, and then I need a lot of outputs. So let me start with doing this and this. Let's say I have 3 states, so I will use QC, QB, and QA. QC, QB, QA are indicating the outputs of the 3 JK flip-flops. And then I have the next state to go to QC plus, QB plus, and QA plus. So after an active edge of the clock, the current state becomes the next state. QC becomes QC plus, QB becomes QB plus, QA becomes QA plus. And then for this, I need to find out JC, KC, the inputs of the most significant flip-flop. Then I have JB, KB. Then I have JA, KA. All right. So that's essentially the skeleton of my state transition table. Now I'm going to start putting things together here. So this current state can be any one of the 8 states. So let me enter these numbers in black. Okay. So I have 0, 1, 0, 1. One, 2, 3, 4, 5, 6, 7, 8. Okay, that's enough. Then I have 2 zeros, 2 ones, 2 zeros, 2 ones. And then I have 4 zeros and 4 ones. So the current state could be any one of those 8 possibilities for the flip-flop outputs. But my next state is going to be dictated by the choice that you made. So after 0, what did we have? After 0, we had 5, right? based on the state diagram, after 0, it should go to 5. So in the same manner, I am going to adjust my state transition table. So 0, 0, 0 should next become 1, 0, 1. After 1, you guys said 7. After 2, you guys said 1. After 3, you had 2. After 4, you had 3. After 5, it was 4. And after 6, oh, 6 wasn't there. So after 6, it was don't care. X, X, X. I don't know. I don't care. And after 7, you had 0. So current state going to the next state for all the 3 bits, the flip-flop outputs, right? And of course, we need 3 flip-flops to do this because we have a 3-bit counter. So let me write that statement down over here. So 3-bit counter implies 3 outputs, 3 flip-flops. Whatever they may be, data flip-flop, JK flip-flop, T flip-flop, we need 3 of them because the output of the counter is what the value of the counter is, right? The output of the outputs of the flip-flops indicate value of counter. So if you have a 3-bit counter, of course we need 3 flip-flops. Coming back to this. So I have to figure out, based on the excitation table of JK, I have to figure out what do I give to JC and KC so that I get a 0 to a 1 transition, right? QC plus 0 to a 1. What should I give at JC and KC? For this, I would need to refer the excitation table. So I'm going to pull up the excitation table on my screen here quickly, and we can talk about that. Let's see here. Okay. So the excitation tables were there in the lecture before this. So let's take a look. All right, based on the excitation table, 0 to a 1 transition can be achieved by setting J and K to be 1x. So I'm going to highlight that as yellow because that's how I got to know that. Next, 0 to 1, 1x. Notice I'm doing this for QC because this is for the most significant flip-flop here. Next, 0 to 0 can be achieved by 0x. Next, 0 to 0, 0x. Next, 1 to 0 can be achieved by x1. Next, 1 to 1 can be achieved by x0. Next, 1 to x, I don't care. 1 to 0, x1. So I filled out for the C flip-flop. Next, move on to QB, going to QB plus, find out what excitation, what input should I give in order for that transition between QB to QB plus. So let's take a look. 0, let me highlight the first one here. Maybe in green. So I need to figure out 0 to 0, what should I give? again using a JK flip-flop. By the way, you could have chosen T here, D here, right? You could have chosen the three flip-flops do not need to be the same. They can be three different flip-flops. We have just made them all the same. All right. JB, KB, what should I give? 0 to 0. 0x. Okay. Next, I have 0 to 1. 0 to 1 is 1x. I think 0 to 1 is 1x. Yes. 1 to 0 is x1. 1 to 1, x0. I'm just referring to the excitation tables of these. 0 to 1, 0 to 0, 1 to x, don't care. 1 to 0, x1. All right, I hope I'm not making any mistakes here while I do this. Now let's come down to the last flip-flop here, QA and QA plus. In order to get that transition, I need to figure out what JA and JA and KA inputs need to be. So I have the first state going from 0 to a 1. 0 to a 1 using a JK flip-flop. I need 1x. 1 to 1, x0. 0 to 1, 1x. 1 to 0, x1. 0 to 1, 1x. 1 to 0, x1. 0 to don't care. 1 to 0. 1 to 0 is x1. All right, I hope I have not made a mistake here. But if I have, I hope you guys will catch me there. Now, once I have my state transition table complete, and all of this is based on the excitation tables here. I need to use 6 3-variable K-maps to write JC, KC, JB, KB, JA, KA in terms of QC, QB, and QA. So that's my next step. Let me go up forward one. Use current template, sure. Step 3. Here we are going to use 6 3-variable K-maps to write JC, KC, JB, KB, JA, KA in terms of QC, QB, QA. So these are all my outputs, right? Sorry. JC, all these are inputs to the flip-flops, the 3 flip-flops. And these guys over here are the outputs of those flip-flops. So as you can see, this is going to take quite a bit, but that's my goal, right? To use those K-maps, 6 of them, so that you fill them up with all these values. Your goal is to write 6 equations, one for KC, JC, KC, JB, KB, JA, KA in terms of the current state variables, QC, QB, QA. Once you write those expressions, based on that, you would make all the interconnections. So after you complete step 3, you are going to get 6 equations. And based on those equations, you would connect things. And I will show you the skeleton of this. But my most significant flip-flop that I was using was flip-flop C, right? So let's see. That's one flip-flop there. I needed 3 of them. So that second flip-flop there and third flip-flop there. And you know, you can also decide whether you wanted these guys to be positive edge triggered or negative edge triggered. I'm just going to make them all a positive edge triggered flip-flop, and I'm going to connect all these guys to one clock source. It's a synchronous design. And let's see, this would be my clock, right? So it's doing up and down here. They're all triggered. Now I can have this to be most significant. So I can say this is JC, this is KC to give me Q and QN. JB, KB, Q, QN, JA, KA, Q, QN, right? I'm not using QN for now, so that's fine. But essentially, if you take a look at the outputs here, you have this output there, you have this output there, and you have this output there, right? And those outputs are essentially what? QC and QB and QA. Those are essentially indicating the counter values. So from step number 3, when you get those 6 equations, you are essentially trying to figure out, suppose this is an assumption here, if JC equals QC and QB, you are essentially putting an AND gate between this guy and this guy and driving it over here into JC. You guys see that? So that's essentially what you're trying to do. Of course, I made that assumption there, which is not true because I have not yet simplified those expressions. But your goal is to find what goes here, 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 what goes here. And so there would be some combinational logic here, that will take the inputs QC, QB, QA and give you the output JC, KC, JB, KB, and JA, KA. And that's how you would figure out those inputs. And once you figure that out, this will become a positive edge triggered counter using 3 JK flip-flops to count in the sequence that you guys have picked out. All right, so what I'll do is I'm going to stop things here.